we're going to go ahead and begin. Hello, everybody. Welcome to our webinar on sensor fusion and localization systems for improving vehicle safety in challenging weather conditions. My name is Eric Glenn, and I am Safety Program Manager. You all have come into the meeting muted, and we would appreciate if you stayed muted until the Q&A session is complete. And stay muted until the Q&A session. Captions will be on for your convenience. Videos will be off during the presentation to maintain bandwidth strength. If you have any questions during the webinar, please type them in the chat box and they will be addressed at the end. Chat box is located in the bottom, center bottom of the screen next to the participants icon. At this time, I'd like to introduce the presenter. Dr. Bassem Vegamore received his PhD from the Department of Mechanical Engineering at Texas A&M University in 2021, having previously obtained his MS from the department in 2018. His graduate research on control and perception for autonomous driving was supported by safety, as well as the Dwight Eisenhower Transportation Fellowship. His research interests are vehicle dynamics, platooning, vehicle-to-vehicle communication, application, and sensor fusion. Now that the introductions are complete, I will turn it over to Dr. Vegamore.
Hi, I'm assuming everyone can hear me okay. If not, let me know. So good afternoon, everyone. I'm Vamsi Vegamore, and welcome to a webinar for the project that was completed towards the end of last year about a sensor fusion system for improving vehicle safety in challenging weather conditions. I think first, acknowledgements are due. So our faculty that was supervising this project was Dr. Sivakumar Ratnam from Texas A&M, and I believe he's in the chat today. I had Abhay Badoria, who was also a graduate student in the mechanical engineering department, involved in this project. So it was a team effort, definitely. And financially, this project was supported, of course, from safety, but also from US Department of Transportation through a fellowship and Texas A&M Transportation Institute. So thank you for that. Okay, so here's an overview of what you'll see today for the next, let's say, 30 minutes or so. I'll try to motivate the project and talk about why we need to look into adverse weather conditions. I'll walk you through what the type of sensors and their configuration that we mounted them to the vehicle. And then I'll talk about object detection and object tracking using some algorithms that if you don't know these acronyms, don't worry about it. I'll talk about them later. And then I'll present some results, some videos on some validation, and then touch on some things that we left out. Hopefully, maybe one of you can continue that work. So I'm sure you've seen this chart in one form or the other. It's the typical 6 levels of automation from SAE. And whatever version of the chart that you've seen, you'll always see that in the highest level, SAE level 5, you'll see that the vehicle has to be able to drive under all conditions. You'll always see this language under all conditions. More precisely, it means that the vehicle needs to function under all drivable conditions. And as we know, the overall goal of self-driving is to eliminate accidents caused from human error. So we want to do better than a human driver always. And so the caveat that comes with this language of all drivable conditions is that the vehicle, car, truck, whatever it is, needs to perceive its environment even in adverse conditions. So you can think about situations like nighttime driving under fog or heavy rain, where it might be difficult not just for sensors but also for humans to drive. But the expectation of a fully functional level 5 vehicle is that it should, be able to perceive the environment, detect obstacles, and perform its driving task even in these conditions. So that's sort of the motivating need for this project. And so what we decided to do is focus on, as I mentioned, the challenge of poor visibility. This is something that's always overlooked in a lot of lot of current implementations, let's say. So you'll see a lot of news about Tesla, Waymo, and all these crews nowadays that have a very limited operational domain, let's say, where they operate, let's say, only in one city or under certain conditions, under certain weather conditions, and they'll just pull over to the side of the road, or they'll not be deployed during adverse conditions. But again, we want to push towards level 5, so this is an important topic to really study. And as we can see from examples such as this, the typical cameras that are used, that's the same type of camera that's in your phone. These are called RGB cameras because they usually represent information in terms of red, green, and blue pixels. If you point them directly into the sun, which could happen while you're driving towards sunrise or sunset, or if you point them at night, you'll see that there's a lot of loss of information. So in this example, this is the case for a sunset. You'll see that there is a car in front, but it's barely visible due to the glare of the sun. And there's actually a car in front of it. Now we're able to see this in the right-hand image because this is actually in the thermal spectrum. So we're using a thermal camera that's mounted to the roof of the car. I'll talk about that. I'll show that in a bit. But we can see that there's a lot of information that we can gain in the thermal spectrum that would have been otherwise lost in the RGB or visible spectrum, let's say. And so you'll see that there are two additional not smaller, but you can see that there are two additional cars in front that would have been easily missed in the regular camera spectrum. And we also know that RGB cameras are unsuitable in fog as well as in light. So at night, so when there are no street lamps, for example, you can barely see the car in front. Let's say the headlights are damaged for that car or the tail lights are broken, you would not be able to see that car at all. Whereas in the thermal spectrum, again, nighttime is not an issue because most cars generally run a little bit hotter than the road, so you can easily pick them up. And so the specific goal of this project was to explore the feasibility of using thermal cameras to overcome these adverse visibility conditions. So if I don't know what the typical structure of the webinar is, but if you have any questions, feel free to throw them into the chat. I'll keep an eye out and try to answer as I go along. So here's the sensor configuration that we used. We were able to leverage 3D printing to design a mount for the camera, and the nice things is you can iterate very fast. So we finally settled on this design where we had 5 cameras oriented in this way. They have like a common focal point, let's say. And with this configuration, we were able to get a total of 190 degrees field of view. So we can see everything in front of the car and then a little bit to the side as well. This was mounted to, so this design, after we prototyped through the iterations, we fabricated it in aluminum, mounted it to the roof of the vehicle. Maybe this picture is not the best one, but there's a roof rack mounted to the vehicle. This is a Lincoln, I think it's a 2017 Lincoln MKZ that we use at our university for prototyping all sorts of self-driving algorithms. So we're using that as our test vehicle. And each of these cameras are from FLIR. They're called ADK, or Automotive Development Kit, and they individually have a 50-degree field of view, which is a little bit narrow for what we wanted. So that was the reason why we have multiple of them, and that way you can get a total wide-angle field of view. Not shown here is a front-facing radar from Delphi. Maybe some of you are familiar with Delphi ESR. It's just mounted to the bonnet of the vehicle in the front. No, sorry, not bonnet, the bumper. And yeah, so those are the 2 main sensors. Of course, there's the vehicle CAN bus that's recorded on board. There's also an IMU and GPS sensor in the car as well. That's also recorded. PowerPoint presentation, I'm not sure. That's probably a question for Mr. Glenn. Okay, so let's move on to the object detection and tracking part. So those are the sensors that we were using. And now the main task, as I mentioned, is to deal with environment perception, right? So we want to make sure that the vehicle can identify obstacles and track them, and track them on the road, right? So for our task, at least, we try to narrow it down specifically to vehicles because As I'll tell you later on, we needed a lot of training and testing data, and there are a lot of cars in Texas, so it's easy to get that. So we narrowed it down to just vehicles. Initially, we were thinking of using pedestrians and bicycles as well, but as COVID hit, classes became virtual, and people, didn't attend in-person classes. So campus became a little bit less crowded. So we just stuck with vehicles after that. And so as I showed, okay. As I showed, we had 5 different cameras, and I'll show you an output of what the stitched video feed looks like in a minute. But what we did for object detection, so there are 2 tasks here, obviously. So there's object detection and tracking. So you have to identify, if you're given an image, you identify where the vehicles are. And then the next step is you have to track those vehicles. So for the detection step, we used something called YOLO, or you only look once. So it's a very common and very famous machine learning algorithm where you can supply any image to it, and it will identify what objects are in the image. So if you, for example, if you give this image, it will identify that there's a dog, there's a bike, and there's a car. There are some caveats with implementing this in our application, so I'll talk about that in a bit. Maybe some of you are already familiar with YOLO. If not, maybe feel free to ask me questions if I'm not doing a good job of explaining it. But what happens is there's something called an input layer in this algorithm, and it's usually a fixed number of pixels. So in this case, I'm showing an input layer that's 512 pixels wide, 512 pixels high. And so now this is fixed. This is based on the algorithm itself, or the trained algorithm. Now you can supply any size of image to it. So the image itself doesn't have to be the same size. So for example, in this image, it's 768 pixels wide, 576 pixels tall. What it will do is it will automatically squish the largest dimension to 512. So it'll, in this case, it'll squish or rather scale the largest dimension to 512. So it'll squish it to it'll squish it in this way. And so if you can imagine trying to just reduce this to 512, this will be 400 something. And so you'll see there's a gap here of empty pixels. Now, this is not a problem. You can still run the YOLO algorithm fine, and it will still give reasonable outputs. But now, as I showed, I think this picture was missing earlier. Sorry about that. But this is what the output of all the stitched camera feed looks like. So this is just a screenshot, but you can see there's actually different banding. That's an indication that it's coming from different cameras, because there was a firmware behavior where the refresh rate was slightly different between the cameras, and there wasn't much we could do about it to eliminate the banding. But this is what the stitched video feed looks like for the 190-degree field of view camera system. And so if you want to run this kind of image into the YOLO algorithm, what it'll do is it'll scale the largest dimension, which is 2,400 pixels by, let's say, 512. So sorry, 512 by 2,400. And so you'll have a lot of empty space on the height. And so this is not really an ideal scenario, because the way these algorithms work, they are trained to identify certain features in order to detect the vehicle. So perhaps a wheel is, for example, a feature, but if your image is scaled down to this size, you really can't pick out anything. So what we had to do was reconfigure the YOLO algorithm and retrain it. And as I mentioned, so very poor performance was observed using pre-trained models. And the other caveat was that usually the YOLO algorithm is meant to be used with RGB images, so red, green, blue pixels at 3 channels. As you saw in the dog picture, it's a color image basically. So it's trained for those kind of images. It's not really well trained for grayscale images, which is what the thermal camera outputs. And so we had to account for that as well. And the way you train these machine learning algorithms is you need to have an annotated data set. So typically, you need to supply a set of images like this, for example, and then you also need to supply some bounding boxes. If you say, okay, pixel x, x1, y1 to pixel x2, y2 describes a car. So that is a description of a bounding box. And so these are annotated. These are called annotated images, and they're pretty hard to get by. But luckily, we found pretty hard to come by for the thermal spectrum. But luckily we found a data set from FLIR, the camera manufacturer themselves. But again, they also have the same problem where they are of aspect ratio 1:1, whereas our images are aspect ratio 5:1 because we have 5 cameras stitched together side by side. And the way we overcame this was to create an artificial data set using these images by sort of padding these black rectangles on either side to make sure that we have artificially now created an image that is 5:1. And then you can train the YOLO network on these images and then use the trained weights to then predict or to detect the vehicles. So this is what the output of the whole process looks like. In case you didn't understand all of that, you can just think, okay, look, this is what the output of the machine learning algorithm that is used to detect vehicles looks like. So you give this image to the algorithm, it will give out these bounding boxes, these green boxes that say, okay, there's a car here or there's a person here. In our case, we trained it on just cars and people. And then, as I said, later on, we dropped the person tag as well. So we just focused on passenger cars. So this is the object detection part. So that's one half of the problem. The other half is object tracking. So now you have these detections. How do you track them? And this is where the problem of data association comes in. So I'll try to explain what the core of the issue is. So as I mentioned earlier, we have now these bounding boxes, which are sort of outputs from the YOLO algorithm. These are now considered a sensor measurement. So it's like the camera sensor is giving you a measurement of where the vehicle is, right? So you can think of it that way. So at some time t=1, you have this measurement, there's a green box. Now at the next time step, t=2, let's say it gives you 2 other boxes, these 2 green boxes, and this yellow box is from the previous time step that you still have in memory. Now the problem is you have now 2 new measurements, but you don't know which of these measurements is associated with this car and which one is associated with this car. This is a little bit exaggerated, and usually these boxes will be closer to the actual car, but you can see, where the issue would lie, because there's now an overlap of this box with both of these, but you don't know which one is associated with what. And this is the core problem of data association. How do you associate new sensor measurements to your existing tracks? So that's the data association problem. And there are a few ways to solve this. I listed 3 of them here. So first is something called nearest neighbor. And the idea is pretty simple. You just take the box that is closest to you using some metric. So for example, if you're in the 2D plane, you can use a metric of distance between the center of the boxes and just pick the closest box as your associated measurement. There's also 2 other methods called joint probabilistic data association, multiple hypothesis tracking. I'll talk about both of them in some detail over the next few slides. But yeah, so this is the tracking part of the problem. To apply these 2 methods, JPDA and MHC, there's some pre-processing of the data that needs to happen, and there's some new words and terminology that I'll try to explain. So what we do with the new measurements, so whenever I say measurements, think of them as sensor returns. So these can be either camera bounding boxes that I talked about, or these could be radar returns from the front-facing radar that I mentioned we had mounted to the bumper of the car. So what we do first is we cluster these measurements using something called validation gates. A validation gate in 2D plane is basically just an ellipse, and so you can imagine if you try to plot these measurements onto the image, they'll be scattered all over. But we first try to cluster them around the track, around the target. So I'm representing T1 as a target, and M1, M2, M3, etc. as the measurements. And T1, the target is what you already have from your previous estimations. For example, in this case, the yellow box represents information that you previously had. So that would be the target, and these green boxes would be the measurements. Now you could have a situation like this where there are two vehicles that are close by, and you have, as I previously mentioned, previously showed, you could have multiple new measurements coming in that overlap the regions that are of interest for those two targets. So, for example, in this case, M5 could either be a new measurement for target number 2, or it could be a new measurement for target number 1. Right, so there's an ambiguity there, and it's not obvious which measurement belongs to which target. You'll also see that in this region, there are multiple measurements that are associated with the target too. But in reality, you know that only one of the measurements is actually associated with that target. So what we do is we classify a dummy target called the clutter. And we say that, okay, out of these three, there's one of them that's associated with the real target, and the other two are associated with this dummy target called clutter. And that's usually represented with index 0. So T0 would be clutter, that's not shown here. And so once you have these clusters that you've identified, you then process each cluster separately. So more pre-processing. What you do is you create something called a validation matrix. You create something called a validation matrix, and this is basically just encapsulating this graphical information into a matrix form. So in this example, you have pre-existing information of tracks T1 and T2. Sorry for the notation confusion, but you have two tracks T1 and T2, and they have some overlapping measurements coming in. So in this case, M2 could be a measurement associated with T1. M2 could also be a measurement associated with T2. And M1, we know that it's only associated with T1. M3 can only be associated with T2 because it's in their own separate regions. So this matrix essentially encapsulates all of that information. So we can go through this a little bit in detail. So the column in labels are what the targets are. So this is T0, T1, T2. As I mentioned, T0 is usually clutter. So which means you can think of this as background noise. And so it's possible that M1 is either associated with T1 or it could be associated with clutter, like background noise. So that's why you'll see in the column 0, there's a 1. For row M1, in column 0, there's a 1. In column 1, there's a 1. It cannot be associated with target 2. So row 1, column 3 is 0. Similarly, M2, which is in the common region between these two, can be associated with any of the targets, T1 and T2. It could also be background noise. So this entire row is 1s, and then similar logic for M3. Now this is something called a validation matrix. And now this is where the JPDA algorithm starts. So as I mentioned before, nearest neighbor, you just pick the closest one. What JPDA does is it essentially takes the weighted sum of all possibilities. And so you have to first generate all different possibilities. So these are the 8 different event matrices or 8 different possibilities. You can think of this 8 different combinations of this cluster. So let's look at maybe 1 or 2 combinations. It's possible that in one scenario, all these measurements are noise and none of them are actually related to the target. So that's why you have this entire column 1s and none of them are actually tied to the targets. Let's look at, let's say this one. It's possible that M1 and M2 are just background noise and M3 is tied to target 2. So you'll see in the first column, there's 2 1s, and then the last column, there's 1, and there's no measurement at that time step for target T1. So this, that's one possibility. So this is actually a very simple case where you just have 3 measurements and 2 targets, and you already have 8 matrices. So you can imagine if you're trying to track multiple vehicles, as I showed in one of the earlier pictures, and if you have multiple sensor returns from radars and camera, then this process blows up. These matrices size blows up, the number blows up, and so it becomes very computationally intensive. And so here's what the equation would look like. It's a bit nasty, and as you can imagine, there's a lot of products involved, so the computation is also pretty heavy. What we do instead is we found this paper from Zhou and Bose. They they came up with the algebraic simplification with the condition that each cluster, there's only 3 targets or less. So, and for us, that actually ended up being reasonable, because when you looked at the data, there's only so many cars that can fit in a given volume of space. So this assumption seemed pretty reasonable, and we decided to go with that simplification. So yeah, so that's JPDA, and I'll also talk briefly about MHT. I don't know if I've lost everyone or not, but hopefully I haven't. So that was one approach. As I mentioned, JPDA is, you can think of it as a weighted sum of all different possibilities. So you calculate all of those event matrices, you calculate the probabilities of those event matrices, and then you take the weighted sum of them to give you the the association for the next step, let's say. Now there's another approach called MHT, which is the acronym stands for multiple hypothesis tracking, and it was proposed in 1978 by Donald Reed. And the idea is pretty similar, but in JPDA, you might have noticed that you have to calculate all of these probabilities, all these event matrices at each time step, and then you make a decision at every time step, and then you have to live with that decision, basically. In MHT, you don't have to do that. You can postpone the decision to a future point of time, and you can basically change your mind, is one way of looking at it. And so what MHT does is, let's say you have these 3 targets, and you got 2 measurements for this target. Let's look at target 1. So at some time step, you got 2 new measurements for target 1. It's possible that it's possible that M2 is associated with target 1. It's also possible M1 is associated with target 1. So it will consider both of these possibilities and create it'll store it in a way. It's called hypothesis. Basically, each of these possibilities is termed as hypothesis in this method. And then let's say at time 2, now you can have 2 more measurements for time 2, J1, J2. So maybe it's better if I just draw. Okay. Yeah, so you can imagine that every time step you're getting 2 new or maybe even 3 new measurements associated. And what we can do is we can create a hypothesis like this. So this, for example, is one hypothesis. What that means is target 1 had a measurement M2 associated at time 1, and it went on to have J1 associated at time 2. So that is one track or one branch of this tree. And you can also have another hypothesis where it went on to M2, but then it went on to J2, and then so on. So you can see how you can have multiple possibilities based on each different measurement that you get. So these are all called hypotheses. And so the way the MHT algorithm works is it generates all of these hypotheses and keeps track of them. And as you can see, even with just 3 time steps, you now have a lot of hypotheses just for 3 targets. And so the downside of this algorithm is that it also blows up exponentially when you have multiple targets and multiple measurements. And so what we did in this as well is we pruned the targets based on a score. So the exact method is described in this paper from Blackman in multiple hypothesis tracking for multiple target tracking. But essentially you assign a score to each of these branches or each of these hypotheses, and then you, at every time step, you just keep the 10 or 15 highest scoring hypothesis in memory and just throw away the rest. And so you can propagate it in this way. So these are the 2 data association or data or object tracking algorithms, let's say. And so this is what the overview of the whole code looks like. So if you want to put everything together, we have the I don't know where my pointer went. Yeah, so we have the cameras, radar, CAN, and IMU information coming in. This is the sensors. You can think of it that way. First step, as I mentioned, we stitch all the images to create a nice panorama with all the 5 cameras. And then this is where the core of the sensor fusion algorithm begins, is you initiate the track. So this, we have done it in a little bit of heuristic way. So we just compare two consecutive images, and if a car appears in both of those images, we assume that a track can be initiated. And so that's what the track initiator block is doing. And then we then use a Kalman filter essentially to propagate these tracks to the next time step. And then and so that gives us an expectation of where the car would be in the next time step. That is, and then we use that information along with the two algorithms that I just talked about, MST and JPDA, to combine the new measurements with the existing tracks, and that's what the track maintenance block is doing. And in this process, we also need to destroy some tracks, because so you can imagine if some vehicle is in view and then it moves out of view. So for example, it took a turn and left the road, then we need to destroy that track. So that's what the track destructor block is doing. And so there's a little bit of a inner loop here for continuously initiating new tracks as vehicles come into view and continuously removing the tracks as vehicles move out. And then finally, we get a set of object tracks. Now, what a track is changeable. In our case, we describe it in terms of some states like X, Y, and I believe the heading angle as well. I'll talk about that in a little bit, but that's the final output of the entire process. Okay, maybe the boring part's over. I don't know, but here's some results of what the final output looks like. So in the top left corner, you'll see what the regular camera sees, right? So this is an RGB camera. In this case, we're driving directly into the sunset, and so it's a very difficult scenario even for human drivers, because you'll have the sun glaring into your face. And oh, can I play this? Okay. And on the right side, we see the raw data that's coming in from the radar. So each of these circles are measurements coming in from the radar, and you'll see there's some background noise. There's sometimes multiple measurements per target. So that's why we need this whole business of clustering and doing data association. And then these are sort of the outputs. So let's say we used only radar information and ignored the camera information. This is how the tracking looks like. And if we combine both of them, this is the final output of what the tracking looks like. So we're able to detect and track the vehicles in front. If you compare that with this image, it would be very difficult to see that there are even 3 vehicles in this image. Then this is another example with all 5 cameras. So you can see the wide angle field of view. It's a bit more jittery. Apologies for that. I think my computer at that time was freezing as I was running this algorithm and at the same time recording the screen. But here's an example basically at night. So this it's not a spectacular camera, but you can see why driving at night poses a problem with not just with low light, but also glare from oncoming headlights, which also will distort and ruin the image from the camera. But in the thermal camera, that's not an issue at all. So yeah, these are videos, and that's okay. But the question would then be how well is the algorithm performing, right? So that's where we need to do some sort of validation. And so we did this a couple of different ways. And first we tried using simulation. So there's something called Unreal Engine, which is a visualization software, and MATLAB happens to have a toolbox that interacts with it. So what we can do is we can design a scenario like this in MATLAB where we say, okay, there are 3 cars. MATLAB represents cars with boxes. There are 3 cars, and these cars are performing these kind of lane change maneuvers. The blue car is the ego vehicle, or the vehicle that you have your sensors and computer mounted to. And so we first design this sort of vehicle trajectory scenario in MATLAB, and then we can feed this into Unreal Engine. which then gives us a much nicer, more realistic video output that looks like this. So we can see there are real cars. And the reason this looks grayscale is because, well, there isn't really a thermal camera model in Unreal Engine because, as you know, thermal cameras work based on detecting temperature, and as far as I know, there aren't really any good simulation software that realistically generate thermal camera data. So what we did is we just took a regular camera model from in the software and just converted that to grayscale. So this is sort of a pseudo thermal image, you can think of it that way. And and so there's also like a virtual radar sensor within MATLAB. So we were able to pull all these tools together to create essentially a digital twin of the back file. So we use ROS, in case I didn't mention that before. We use ROS on our vehicle platform to collect all the sensor data and we store them in something called bag files. And so what we were able to do was, even in the simulation, we were able to create a digital twin of the bag file that had the camera, radar, IMU, and vehicle CAN signals. And so we don't have to make any changes to our algorithm. We just we just replace the real world bag file with this simulated bag file, and we can test the algorithm with the advantage now that we now have the ground truth of the exact positions of these vehicles. So if you want to validate this algorithm, usually what you need is the ground truth of the exact positions of all the vehicles around you, which is not possible to measure in the real world because you need to stick a GPS sensor on every car on the road. So, but we can do that in simulation because we design the trajectories of all the other road vehicles. And there's a toolbar, a Python library called PyMOT-Metrics. So this essentially looks at compares the output between the between the output of the fusion algorithm and the ground truth. So this is what the output text file looks like for both of those. So in each, it's basically a bunch of lines that have this format, and the lines are structured in this way. So there's a frame ID. So you can think of this as the camera frame number. So if you have 15 frames per second, you'll have 15 lines per second generated. Track ID is the vehicle identification number. XY is the position of the vehicle in the camera frame. And then width and height is the length of those green bounding boxes that I'd shown earlier. And so we then, so the sensor fusion algorithm generates a text file that looks like this. We know the ground truth from the simulation. So we compare those two text files, and there's a standardized multiple object tracking score that is generated from this library. And so these are what the scores look like for JPDA and MHD, just to give some reference for what these numbers are. You can think of precision as how precise the width and height of the bounding boxes are versus the ground truth, and the recall is sort of if at all the bounding box is picked up or not. If it completely missed the detection, then you'd have a poor recall score. If it picked up the detection, but it wasn't giving you the correct dimensions of those green bounding boxes, then it'll give you a poor precision score. And these are the scores that we got for the two algorithms. The MHD algorithm did significantly better. And just as another point of reference, I've seen some benchmarks where these scores are around the 75% and 50-55% marks. So these are not spectacular, but they're comparable to what's out there in literature. So that's validation using simulations. We also tried, but couldn't complete the validation using real world data. So what we did was we attached a LiDAR sensor to the roof of the car. And in the LiDAR, you can actually track these vehicles. So you can see, for example, this car here corresponds to this LiDAR point cloud. But the problem was that since the cameras were front facing, and they were able to pick up cars that were really far away. So you can see these were like maybe 20-30 pixels wide, these bounding boxes, and it was able to detect that it's a car. But in the LiDAR point cloud, the LiDAR sensor isn't able to, I guess, send its beam that far away. So in terms of using the ground LiDAR as a ground truth, it wasn't really that functional. So we had to drop that idea of validation using LiDAR. And there's also another challenge that we wanted to address. I think it was initially part of the plan, but we were planning to use an artificial rain tunnel to study how well the thermal camera system behaves during heavy rain. And when I say heavy rain, I mean a scenario where the fastest speed of your wiper blade is not enough to clear the water. So like thunderstorm kind of rain. And it's interesting because LiDARs, we know that they don't do very well in heavy rain, that kind of heavy rain. And cameras, of course, you're limited to whatever you can see through the windshield. So we wanted to see how a thermal camera would perform. We had some preliminary data, I would say, where there was an issue with in the thermal spectrum, because you can imagine if it rains heavily, all of the surfaces, including the cars, bodies, and the road, are covered by water, and so they all become the same temperature, and it was very difficult for us to detect a car from the identify a car from the background in thermal spectrum. But I think that's still a bit of an open problem, and I think it's an interesting challenge to address if anyone is interested in picking it up. Sorry. Yeah, so we weren't able to finish our real-world validation with LiDAR, primarily because the LiDAR sensor that we had was not didn't have sufficient range to validate the measurements that the camera was able to pick up. And another thing that would be nice is, as I mentioned, we had a front-facing radar, but that only had a field of view of 120 degrees, while the camera had a much larger field of view of 190 degrees. So it would also be nice to add additional side-facing radars to, so that there's a good overlap between both the sensor modalities, and probably that will help in better performance of the sensor fusion algorithm. So those were some of the challenges / future work items that I wanted to talk about. So in terms of deliverables, these were the main things. So there's a final report. We had a conference paper that was published in 2021. And maybe more important and more interesting for the audience might be the data set that's the raw SPAC files that have all the thermal camera images, high resolution data, vehicle CAN data, IMU radar, and even the RGB camera. And that's available on the VTTI website. These are pretty large files, so just a warning there. And this specifically includes some nighttime driving as well as driving into the sun during sunset, sunrise. Yeah, thank you for listening. I'll be happy to answer any questions. I see one question: how very cold temperature affect the detection output? I don't know if that's going to be a significant problem, because again, cars usually run hotter than the road, right? So in fact, I think it'll be an advantage for thermal cameras, because you'll be able to pick up the car even more easily in winter. I don't know if that answers your question. I
also have another question that was emailed to me. So is there a possibility that this technology could be adapted to sense the presence of wildlife on roadways and in the right way?
Yeah, definitely it can be. So yeah, warm-blooded animals will show up pretty easily on thermal cameras, especially at night. Part of the reason why we limited ourselves in this project to, for vehicles is we are able to go out on the road and collect vehicles and test the algorithm pretty easily. It would be harder to find wildlife on roads, but yes, it's definitely a good application. And if I'm not mistaken, I think there was one prototype of some BMW vehicle a few years back that did something similar, where they would detect wildlife at night and use that for emergency braking or something like that. Yeah.
Okay. And speaking of OEMs, there's another question that was emailed to me. It's based on this study. What do you think of Tesla's camera-only approach for self-driving?
Yeah, I mean, Tesla is always a fun topic to debate. I would say, at least my opinion, I think you need, for full level 5, you probably need more than just one sensor modality. So you need more than, at least you need more than one type of camera. So it could be maybe an RGB camera plus a thermal camera or something else. Yeah, I think it would be quite a bit of a stretch to use just one type of sensor to get to full level 5, but that's it. Maybe I'll eat my own words 15 years later. I don't know, but that's my opinion as of now.
Okay. And if there are any other questions, feel free to unmute or continue to write them in the chat box.
Is there any like control over emissivity or something like that that could help with the rain detection, do you think?
Sorry, could you say that again? Emissivity in terms of?
Yeah, like is there a ability to control for different emissivities of whatever you're detecting?
In the thermal camera?
Yeah, to try and boost the rain detection.
That's interesting. Yeah, it might be possible. I don't know. We have not tried it, and yeah, that might involve some firmware changes. So yeah, but that's a very interesting way to address that.
Yeah, I know in some instances, like plastic will respond different to aluminum than to steel, and you've got to like configure your camera accordingly if that's what you're trying to detect. So it'll be difficult to pick one thing to set for everything, but yeah.
Oh, thank you for the suggestion. Yeah, that's a good point. Why YOLO? Are there alternatives? Yeah, definitely there are other alternatives. I'm sure there's like a new paper published every week about object detection with images. But yeah, I just picked YOLO because not only was I new to the topic, it was also the most commonly well used. So if I needed support, I could just ask people or search for help online. That was my main reason for using YOLO.
Could you use this technology to count vehicle lane changes during day and night time?
Sorry, could you please repeat that again?
Could you use this technology to count vehicle lane changes, either in the day and night, both?
Yeah, sure. Yeah, I don't see why not. As I said, if you have like a thermal camera or mounted to a street light looking down, I think it'll do pretty well. Even at night when there's poor lighting, for example, it'll be able to pick up the car against the road and yeah, measure lane changes as well.
Good. Thank you.
Thank you.
Kind of more of a tangent thought again, but do you think like electric vehicles being significantly less heat generating would be potentially more difficult to track?
I'm trying to think if we had any Teslas in our data sets. Maybe not. I didn't really look for the brand, but yeah, I don't know. When I say heat, I don't mean just like the engine compartment. What I've seen, I mean, you can see even in the images, right? So yeah,
imagine the tires and wheels will be pretty bright.
So you can see like there's the wheel hubs and the underneath part of the car that gets hot as well. So yeah, I'm sure there's probably some reduction in heat generation, but you can see really clearly the wheels are the ones that are really hot because they generate a lot of heat from the tires. I don't think it should be a huge problem, even if it's electric. I suspect this might be a price. I'm not sure. Maybe not. But yeah, that's an interesting question.
We have another one from Ali. Can you elaborate more on the number of targets? I recall it was 3 or less.
Yes, so these are 3 or less targets per cluster. So what that means is, so for example, if you look at this group of vehicles, there's 3 or less in this group. There's 2 in this group. So those ellipsoidal regions that I showed, you can define them based on some heuristics or by trial and error. You can define the regions. I said only these 2 fall into one cluster. And so that's what I meant when I say there are 3 or less targets per cluster. It doesn't mean that there's 3 or less targets in your entire field of view. So you can, the idea is that you can process these clusters independently. So you can track these clusters independently from this cluster or this cluster, something like that. If that makes sense.
I have a question. Are you bound by ADT, or does it become inefficient to try to get real heavy ADTs?
I'm sorry, I don't know what ADT is.
Average daily traffic volume.
Well, so I think the primary application for this is for the sensors to be mounted onto the vehicle rather than infrastructure.
No. What I mean is that the more traffic out there, the more conflict you can have with the tracking individual vehicles. So
I see.
Is there a maximum operational constraint in terms of how you can gather this information from a real situation, real road?
I don't really have a number, but I think, again, it probably goes back to that assumption we made that there's 3 or less targets per group. That said, if you're in a lot of heavy traffic, you're not going to have very fast moving vehicles, presumably, right? So I don't think from a practical perspective, it shouldn't be an issue. You'll still be able to track these vehicles because they'll be much closer, and so you can actually say each vehicle is its own cluster, and that wouldn't cause any issue with the assumption that we made. So no, I don't. To answer your question, I don't think there's a hard limit because your sensors are tied to the car, and there's only so many number of roads that will fit in 3 lanes, right? Sorry, there's only so many number of cars that will fit in 3 lanes.
Yeah, but you have longitudinal aspect of the issue too. So you can have a lot of cars packed together in a short distance, for example, on a freeway under heavy volume conditions.
Right. Okay. I think I get your point. That's true. But again, for driving perspective, we're mostly interested in maybe the immediate car in front of us, or maybe one car in front of that, right? We don't really need to track a car that's like 4 cars in front of us. Does that?
Well, you're sort of getting there. What I'm thinking about is that you have situations where you've got these idiots that like to go lane changing in and out from the median lane to the shoulder lane, all the way down the road to try to get ahead of the queue. And so you get a number of vehicles there packed together, but you have this one fool that's doing all this foolishness. And you would like to be able to see how often they're doing that in a limited amount of space, whether it's 1,000 feet or whatever.
Yeah,
it might be pushing the limits of the technology. That's what I'm
I would say it's pushing the limits of like compute power. So the primary reason why we put that assumption of let's only have 3 targets per cluster is the computer that we had would not be able to run fast enough if we were trying to track too many cars, let's say. So yeah, it really, I think bottom line is like how powerful of a computer do you have?
Okay, all right.
It's not limited necessarily by the sensor.
In theory, it'll work, but you've got to be able to have the computer strength in order to do it. Power.
Yep. Yeah, to track a lot of vehicles. Yeah.
All right. Thank you.
Thank you. Can you talk more about how to add track targets? No previous measurements from Mike. Yeah, so that's a track initiation step. Yeah, and you can. There really isn't like a fixed method to do this. We came up with a heuristic where we say, okay, we compare 2 or 3 consecutive images. So for example, you have an image like this, then a next image that looks similar to this, but the cars might be in a slightly different position. And what we do is we compare the bounding boxes across those 3 images. If that bounding box persists across those 3 images, we we say, okay, there is definitely a car there, and then we initiate the track. And the condition there is that the center of those bounding boxes across those 3 images should be within some threshold. I forget what the exact number is, but you can clearly imagine if there's 3 such images and 3 such bounding boxes, and they're all roughly in the same position with respect to the image, then you can say, okay, there's definitely a car there. Does that answer your question?
Yes, it does.
Okay. Anything else?
This was only tracking X, Y in the camera frame. Is there no depth information, or would that just be another layer of calculation?
So we actually have depth information from radar, but at the end we sort of decided to drop that and just stick with XY. But yes, we can get the Z direction or the X direction technically from the radar, and then these are like, I think the SAE standard, this is like Y and Z or something like that. Yeah.
Yeah, I don't know if that might help with some of the spatial clustering. Most all the vehicles are going to be stacked in front of each other longitudinally. So having some estimation of depth might help in tracking and clustering.
Yeah, there's definitely improvements to be made. The problem with using radar data was that it was quite noisy. So, even if you have just one car in front of you, it would sometimes show 2 or 3 different returns for the same car, and those returns were not smooth. They were noisy. They would be jittering around all the time. So so we placed more weight on the camera measurements rather than the radar returns. But yeah, that radar definitely has its place in in terms of getting depth information, which is then has time to get really sophisticated algorithms implemented. But yeah, you're right. There's definitely an additional way to improve the algorithm. Okay. Yeah, that's about it. If no other questions. Hello.
Can you hear me?
Okay, now I can hear you.
Perfect. Yes. So saying congratulations again for graduating in December. And I just wanted to give you a chance to just let everybody know what you're doing now since you've graduated.
Yeah, so I'm currently working for Goodyear in the tire intelligence department. I moved all the way to Midwest inexplicably from Texas. But yeah, I'm working for Goodyear. It's a short answer.
Congratulations.
Thank you.
All right. Well, just want to thank everybody again for attending this webinar. This webinar will be uploaded to YouTube, and I will know everybody via email when that's complete, along with the PowerPoint being shared to you as well. Be on the lookout if you are part of our email list for the next webinar coming up. And again, thank you all for attending. Really appreciate everybody here. Thank you again to Dr. Vegamore, and congratulations on your job at Goodyear and your move out to the Midwest. Happy Friday, everybody, and have a great weekend. Bye-bye.
Thank you for attending. And yeah, thanks for hosting.
Good job.
Thank you.